Hello everyone. So today we're talking about growth and decay models. When I say growth and decay models, we are talking about growth as in growth of cells or a population, and we're talking about decay, we're talking about radioactive decay or carbon dating. We'll get more into carbon dating tomorrow. So you will need a calculator, so please make sure you have your calculator out so you can try putting these things in your calculator. Make sure you're getting the same answers. If you're not, please send me an email or a my message and I can send you a quick video on how to put things in your calculator. Okay, so with growth of cells or population, we are using this formula right here. If you look at it, it should look pretty familiar. It should look very similar to the PERT formula, and that's because it is the PERT formula. It's just that we use A naught. That's what the sub-zero means right there. So this is A naught. We use A naught for initial amount instead of P, but it's the same exact thing. So this is also called the exponential law, the law of uninhibited growth. So if you see those words, just know you're using the PERT model. Radioactive decay, if you look at it, it is also PERT. So the difference between the two is that this is for, the growth is for values, the rate is greater than 0, and then for decay, the rate is less than 0, which makes sense for growth versus decay. Okay, so let's look at example 1 here. It says the population of a city is given by the equation P equals 110,500 times e to the 0.015 t, where t is the time in years with t equals 0, corresponding to the year 1990. Question number 1. What was the population in 1990? So here's our equation. We could plug in 0 here and see that we get 0.015 times 0 is 0. E to the 0 is 1. 1 times this is this. Or you can say, oh yeah, that's the initial amount, which is what we would like for you to do. So the initial amount of people, 110,500 people. All right, next part. According to this model, in what year? T. Will the population of the city reach 150,000? So very similar to what we did yesterday. So we're going to say we know our final amount. We want to know when it's 150,000 equals our initial amount, 110,500. E to the rate times time was 0.015 times t. Okay, so now we have to solve for t. T is an exponent. To solve for an exponent, we use the inverse of exponents, which is logarithms. In order to log both sides, we have to have the base and the exponent isolated. So step number 1, divide both sides by 110,500. Now go ahead and pick up your calculator and put this in your calculator. What you should notice is that you're getting an irrational number, a number that doesn't have a nice rounding to it. So what we're going to do is not do anything. We're just going to leave it as a fraction. So 150. In fact, you know what you could do though, is that both of these have 2 zeros on the end. You could cross off some zeros just to get the numbers a little bit smaller. That's what I'll do. 1,500 over 1,105. Now that's still reducible more, but hey, I'm not going to do it. It's just more work, and I'm going to end up putting this in my calculator anyways. All right, so now I'm ready to solve for that exponent. I'm going to log both sides, but once again, since it's a base of e, don't use common log, use natural log. Remember that exponent 0.015t I can write in front of my logarithm. In fact, I'm going to move it over and write it bigger so it doesn't look like it's an exponent or anything. It goes 0.015t. It's multiplication here, right? Natural log of e is 1. So to get t by itself, I'm going to divide by 0.015. Divide by 0.015. Go ahead and put that in your calculator. Make sure you close the parentheses on that natural log if one opens here. All right, this is your time. We are going to round to the nearest thousandth for time. We round to the nearest thousandth always, unless it's money or people. So 20.375 years. Now let's make sure we answer the question. In what year will the population reach 150,000? Well, this is not a year, so we still have to write down that year. So we have 1990 plus 20.375, which is 2010.375. So I'm going to say during the year 2010. I want to say during and not just 2010 because the first day of 2010, the population will not be that high. Okay, next one, same idea. The population P of a city is given by this equation where T is the time in years, with T equals 0 corresponding to the year 1990. That's not how it always is. It's just how this problem is also. In 1945, the population was 1,350. Find the value of R and use this result to predict the population in the year 2025. Okay, so for this problem and pretty much every problem after this, you have to realize that you're always going to be missing something and you need it to answer a follow-up question. So what I'm always going to do is I'm going to highlight the follow-up question so I realize that I'm not using that information until I find the missing value that was missing. So this one tells me find the value of R. We're going to stop telling you what you're missing and you're going to have to figure it out yourself very shortly. Use this result to predict the population. So we are predicting the population in 2025. So that's the follow-up question. So what I'm going to do is I'm going to do everything else leading up to that. So I'm going to write my equation here. I know that the population was 1,350 in the year 1945, where my original formula is 2,500 times e to the rate times time. So notice they did not give me the rate, and that's why they're asking me to find it. So I'll put R right here, times. And then the time, 1945 is 45 years before 1990, so negative 45. All right, I have to solve for R. So first things first, divide both sides by 2,500. Pop that in your calculator. This time you'll see you do get a nice answer. So I'm going to write down that decimal instead of leaving it as a fraction. 0.54 equals e to the negative 45R. Natural log both sides. Notice I'm taking that step of writing the exponent in front right away. Totally allowed. And then divide both sides by negative 45. All right, so now we have R is equal to, and I could put that in my calculator. Go ahead and put that in your calculator. You should get 0.01369, so on and so forth. Now I wrote down a bunch of digits just to make sure that yours matches mine, but I want you to realize that this is not our final answer. We haven't found the population in 2025 yet, so we're going to have to use this. Therefore, we want to store this as X in our calculator. So remember, look for the button that says stow on it. Click that, and then you can click as X, the variable. Then when we need to use it, you can just hit X. Okay, so now we are ready to predict the population in 2025. So I want to know what P is, and I'm just using P because that's what they use. If you're using A, that's absolutely fine. P equals 2,500 times e to the R, which is my stored X value. So what I'm going to do is I'm going to put R here, but I'm then going to cross it off and put X stored value. Now, you don't need to write that down every single time, but it's just so that you know that's what it is, times, and then my time. So I want to know what's the population in 2025. That is 35 years after 1990, so I'll put a 35 there. All right, now I'm ready to pick up my calculator again. I'm typing 2,500 e to the your stored x value, so x times 35, enter. Now remember, this is people, so we're going to truncate our answer, meaning chop off the decimals, and you should have 4,037 people. All right, next two right here, very similar. This one is also about population. It says the population of Witten follows the exponential law. That just means use PERT. If the population doubled in size over a 54-month period and the current population is 18,000, what will the population be 5 years from now? So once again, realize that this is a follow-up question. We're not using the 5 in the problem until we find what's missing. All right, so let's look at the PERT formula here and say, do I have a final amount and do I have an initial amount? The current population is 18,000, and I also know that it's doubled. So yeah, I got both of those. E is a constant. It's always in my equation. I don't have to worry about that. My rate. Did it tell me my rate? Nope. Time. Did it tell me my time? Yes. So I first need to solve for rate. So I'm going to say my current population is 18,000. It doubled, so that means that the initial population was 9,000, times e to the rate, which I'm solving for, times time, which is not 54. 54 months is not what I use. I use years. So I have to do 54 divided by 12 to get how many years this is. That's 4.5. So 4.5 is my time. All right. Divide both sides by 9,000. I get 2 is equal to e to the 4.5r. Natural log both sides. Natural log of e is 1. Divide by 4.5. This will give me r. Go ahead and put that in your calculator. You should have 0.15403 ... Keeps going on. Remember, you're going to store this as x because it's not your final answer. And now we're going to go ahead and get our final answer. What will the population be 5 years from now? So there's two ways to do this. If it's 5 years from now, remember the population now is 18,000. So I can use 18,000 and 5 as my year. Or I can use 9,000, but realize it was 4.5 years ago, so I'd have to use 9.5 as my year. I like the first option better. So I'm finding the population. The current population is now 18,000 times e to the, my stored x value, times my time, which is 5 years from now, so 5. Once again, this is my stored x value. I can put that in my calculator, 18,000 times e to the x times 5. Remember, every time you store a value as x, it saves over your old stored value. Truncate your answer, and you should have 38,882 people. All right, bacteria growth. A culture of bacteria obeys the law of uninhibited growth. PERT. If there are 100 bacteria initially and there are 300 after 5 hours, estimate the time required for the population to double in size. So, this is all too real right now, isn't it? But let's do this problem here. So, initial amount, 100. Final amount, 300. Time, 5 hours. Rate, missing. Follow-up question, estimate the time required for the population to double in size. So I want to know what t is after I'm done with that. Okay, so let's start this problem here. So let's write our original equation so that we can figure out what the rate is. So we have our initial amount is 100. It becomes 300. Don't know what the rate at which it's increasing is after 5 hours. Divide by 100. 3 equals e to the 5r. Natural log both sides. Natural log of e is 1. Divide by 5. Get your rate by putting that in your calculator. You should have your rate is 0.21972, so on and so forth. Store that as x. All right, so now if you look at what the question says, it says estimate the time required for the population to double. So how much will the population be when it doubles? It'll be 200. So as we're thinking about this problem right here, what you have to realize is that we know that it takes 5 hours to get to 300. So our answer is going to be less than 5 hours. We should at least be thinking about these things before we do this problem. All right, divide both sides by 100. I get 2 equals e to the r times t. Natural log both sides. Natural log of 2 equals r times t times natural log of e. Natural log of e is 1. You might be looking at this right now and saying, there's 2 variables. What do I do? It's because this is your stored x value, right? So we're trying to get t by itself. So now divide both sides by r. And now I can put natural log of 2. If a parentheses opens, make sure you close it. Divided by r. And that'll give me the time it takes for the population to double. Should get 3.155 hours. Now, if you remember from yesterday, we said time is usually in years. If it's about bacteria growth and they're talking about hours, you do not have to convert hours to years. Okay, next we have decay examples. So we'll get into this a lot more tomorrow. But this is actually really what's current in the current times right now. It's talking about half-life. If you don't know what half-life is, it's the amount of time it takes for a radioactive substance to decay to half of its original value. So if you've watched the news at all, we've been hearing a lot about the half-life of COVID-19, and meaning once it's in the air, how long, what is its half-life? Meaning how long does it take for half of it to be there? And usually a half-life of 4 cycles will get something to no longer exist. But it's crazy to see that what we're doing now in math is applying to what's, they talk about on the news right now. But it's also interesting to understand it and being able to explain it to people who maybe don't understand. So let's go ahead and do a couple problems that have nothing to do with COVID-19 because these notes were made well before that was a problem. All right, so this one says GBN 990, clearly made up. Okay, a newly discovered radioactive material decays according to the equation A equals the initial amount times e to the negative 0.063 t, where A naught is the initial amount and A is the amount present in t years. What is the half-life of GBN 990? Okay, so did I give you an initial amount? Nope. So if I didn't give you an initial amount, A naught is still in the problem. Did I give you a final amount? Not an actual number, but half of the initial amount will be left. So I'm going to write 0.5 times A naught. You could also use 1/2, obviously, that's equivalent, times e to the negative 0.063 t. Whenever I'm asking you what's the half-life, half-life is time. So you're solving for t when you see what's the half-life. Okay, I need to solve for t, which is an exponent, but that means I need to get the base and the exponent by itself. So I'm going to start by dividing both sides by A naught. Divide by A naught, divide by A naught, and you can see that it's no longer there. Now you have 0.5 is equal to e to the negative 0.063 t. Natural log both sides. Natural log of 0.5 is equal to negative 0.063 times t times natural log of e. Natural log of e is 1. Divide by negative 0.063. Divide by negative 0.063. Put that in your calculator. Make sure you're putting 0.5 or 1 divided by 2. Either one's fine for 1/2. And this will give you your half-life. This is a year. We are going to round this to the nearest thousandth. 11.002 years. If you didn't pause the video and try to make sure you can get that, just do so right now. All right, next one says, given an initial 100 grams. So now I'm telling you, okay, well, I have 100 grams of GB990. Use its half-life to determine the amount remaining in 11 years. All right, so today, there's 100 grams. 11 years from now, how much is left? Half, 50 grams. 22 years from now, how much is left? Half, 25 grams. 33 years from now, how much is left? Half, 12.5 grams. That's what half-life means. Algebraically, how long will it take for 100 grams of GBN990 to decay to 35 grams? So we have 100 grams. We want to know when there's going to be 35 left. Times e to the negative 0.063 times t. So what I can tell you about this is that 35 is in between these two, so my answer is somewhere in between 11 and 22 years, but we can solve to get closest to the answer as possible. Divide both sides by 100. Put that in your calculator, but do you really need to? It's 0.35 equals e to the negative 0.063t. Natural log both sides. Natural log of e is 1. Divide by negative 0.063. Divide by negative 0.063. Put that in your calculator and see how long it takes for it to decay to 35 grams. The answer, 16.664 years. All right, the very last one here, and then we'll do some more practice tomorrow. The half-life of radioactive radium is 1,620 years. What percentage of a present amount of radioactive radium will remain after 100 years? So if you look at what we were given, did I give you the initial amount? Nope. Did I give you the final amount? Technically no, but yes. Half of the original amount. Did I give you the rate at which radioactive radium decays? No. Did I give you the time? Yes. So once again, I need the rate at which it decays so I can answer the follow-up question. The follow-up question being, what percentage of a present amount of radioactive radium will remain after 100 years? So what I'm highlighting in red here, whenever I see a sentence such as the half-life of blank is blank years, I can always solve for the rate using that information. So let's go ahead and do that. My initial amount, I don't know how much I have, but I know that there's going to be half left if it's a half-life. Times e to the, I don't know the rate, times the time, 1,620 years. Divide both sides by a naught, they cancel. Natural log both sides. You have natural log of 0.5 is equal to 1620 times r times natural log of e. Natural log of e is 1. Divide by 1620. Divide by 1620. This is going to give me my rate. Put that in your calculator. In your calculator, you should see negative 4.27868, so on and so forth. But then there's an e negative 4 on the end. So this at first looks like a huge rate, but then you realize you have to move the decimal 4 places to the left. So it's actually a really, 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 really slow rate. But you can leave it like that. Your calculator will just store it the way it is. Okay, now I can answer the final question. What percentage of a present amount of radioactive radium will be left after 100 years? Okay, so I'm going to start this the same way. Do I know the original amount? No. Do I know the final amount? No, but I know that I want to know what percentage. So this is like my unknown. Like, is it 50%, like a half-life? Is it 40%? Is it 20%? What is that? That's what I'm looking for. Oops. Times e to the, your rate, which is stored in your calculator, times your time, which is 100 years. So this time, this is right here. Okay, so I need to solve for x. So I need to get x by itself. Realize it's x times this. So I'm going to divide both sides by a naught. Cancels. And I have x equals e to the stored rate times 100. Pick up your calculator. All I have to do is type in e to the r, which is my stored x value, times 100. That gives me 0.95812. So remember, it asked you what percentage, so make sure you move your decimal over 2 places to the right. 95.812%. All right, that's it for today. Tomorrow